Classic macroscopic physics assumes motion is continuous. We expect a particle traveling through an empty vacuum to follow a clean, deterministic, perfectly smooth trajectory. Zooming into the microscopic scale reveals a different reality. True motion is a chaotic, jagged sequence of discrete jumps. Boundary condition quantum mechanics, or BCQM, treats the quantum wave as an informational field that constrains a single realized particle thread. Within this framework, jitter is unavoidable, persisting even in a vacuum at absolute zero. This stochastic residue is the underlying inertial noise of emergent spacetime. Reality lacks a smooth foundation. The structure of spacetime carries an irreducible noise floor that is physically measurable. Simulations of this effect show exactly how localized, random deviations accumulate along a path that only appears straight from a macroscopic distance. This Uther has a deeply structured frequency distribution, serving as a physical fingerprint of spacetime's underlying mechanics. This power spectral density graph maps fluctuation intensity across timescales, transitioning from a stable plateau to a downward slope. This distinct corner frequency identifies the data as a mathematical artifact of the system's mechanics, distinct from environmental interference. This reveals a structural mystery. How does deterministic physics emerge, and what dictates this frequency signature? Understanding the noise requires explaining the smooth drift first. This is the concept of emergent inertia. BCQM defines mass as a derived property of a system, rather than an intrinsic characteristic of a particle. Imagine a particle as an internal quantum clock, ticking in proper time. As it moves, it continuously samples the environmental correlation spectrum along its world line. This environmental interaction creates a feedback loop that resists changes in velocity. We experience this resistance as inertia. These interactions are limited by the coherence horizon. This boundary dictates the temporal extent of recoverable quantum interference. The effective mass of a particle is strictly inversely proportional to the square of this coherence horizon. Inertia is a derived result of a quantum system sampling its environment within its coherence horizon. If the coherence horizon produces smooth inertia, we must account for why the microscopic trajectory remains so jagged. Beneath continuous spacetime lies the graph phase stochastic engine. This is the discrete mechanism that generates realized events. A particle's next position is never predetermined. The engine selects it step by step from a local, hop-bounded menu of probabilistic options. The Langevin equation describes this behavior. The terms on the left represent the smooth, deterministic physics we typically calculate in an emergent spacetime. The final term on the right is the noise term. This represents the unavoidable stochastic residue produced by the selection engine. Because the coherence horizon truncates information, perfect finite-time reversal is impossible. This information loss locks intrinsic jitter into the world line. The act of generating a spacetime event leaves a permanent jittery trace on every realized path. Validating this engine as the source of the noise requires returning to the power spectral density graph. This specific noise profile is universal across a broad class of microscopic graph phase models. The corner frequency scales exactly with the inverse of the coherence horizon. The amplitude of this noise is mathematically locked to the effective mass of the particle. Changing one necessitates a change in the other. Both deterministic mass and stochastic noise emerge from the exact same boundary condition. There are no independent variables. This PSD signature offers a falsifiable prediction. If the graph phase engine builds reality, this fingerprint must be measurable. This raises a question of scale. Why doesn't this jitter average out and disappear for large macroscopic objects? We have to look at entangled clusters, groups of particle threads whose future options are constrained by a single joint propensity structure. BCQM maps these clusters onto a configuration space graph, treating the collection of threads as a single evolving point. Joint moves on this graph must strictly preserve conservation laws and avoid faster-than-light signaling between the components. In tightly bound objects, internal rearrangements relax quickly. As a result, the center of mass of the entire cluster inherits the underlying graph noise. The macroscopic cluster acts as an effective particle. It possesses its own composite coherence horizon and a corresponding scaled-up mass. Macroscopic objects aggregate space-time noise, carrying the signal up to a scale where high-precision instruments can detect it. This shifts BCQM from theoretical math into the high-precision laboratory. Physicists currently cool high-Q optomechanical oscillators, devices that couple mechanical motion to light, down to their absolute ground states. By subtracting known thermal and environmental interference, researchers attempt to observe perfectly smooth physical behavior. BCQM predicts that even as instruments achieve perfection, they will hit a hard, irreducible acceleration noise floor. This signal cannot be shielded or cooled away. It represents the noise floor of space-time generation itself. The chain of causality is fixed. The coherence horizon generates the emergent mass, which inevitably dictates the inertial noise. BCQM offers a specific structural target for experimental physics to investigate. Detecting this specific PSD knee would provide the first direct evidence of the discrete mechanics that build our physical reality. This perspective requires us to stop viewing spacetime as a smooth, pre-existing stage. We must view it as an active, discrete process. Deterministic physics represents a coarse-grained average. The underlying reality is a sequence of discrete quantum events.